Students, welcome back to Abhi online classes. Today we are going to start a new chapter, that is eigenvalues and eigenvectors. B.Sc final year topic it is letter A, Aij, order n by n, be any n-rowed square matrix. This is a square matrix, so number of rows and number of columns are same. And lambda an indeterminate. The matrix A minus lambda I is called characteristic matrix. This is a characteristic matrix, and I is the unit matrix of order n. The equation that A minus lambda I equal to 0 is called characteristic equation of A. This is the characteristic equation, and the roots of this equation and the values which are satisfying this equation are called eigenvalues or characteristic roots or characteristic values or latent roots or proper values of A. So there are so many names. The roots which are satisfying this characteristic equation are called eigenvalues, eigenroots, characteristic values, characteristic roots, latent roots, proper values. All these are same. The set of eigenvalues of A is called spectrum. So in competitive exams we are observing so many questions are asking regarding this topic. That's why I have taken this topic today to cover more important questions. Very important note here is, if lambda is a characteristic root of matrix A, then det A minus lambda equal to 0, then the matrix A minus lambda I is a singular matrix. Then the matrix A minus lambda is singular because det equal to 0. If the determinant of this matrix is 0, then that matrix is singular. So like that they used to ask the competitive exams questions. Therefore, there exists a non-zero vector capital X such that A minus lambda into X equal to null matrix, or Ax is equal to lambda X. Now we see the definition of characteristic vector. If lambda is a characteristic root of n by n matrix A, then a non-zero vector capital X such that Ax equal to lambda into X is called characteristic vector. If lambda is a characteristic root of matrix A, then there exists a non-zero vector capital X such that Ax is equal to lambda X, or A minus lambda I into X equal to null matrix. Then that non-zero vector is called characteristic vector or eigenvector. We can call any name, characteristic vector or eigenvector of A corresponding to the characteristic root lambda. Two important notes I want to remind you regarding this topic. If X is a characteristic vector of matrix A corresponding to the characteristic value lambda, then K into X is also a characteristic vector of A corresponding to the same characteristic value lambda, where K is a non-zero scalar. If X is a characteristic vector of A corresponding to the characteristic value lambda, then K into X is also a characteristic vector of A corresponding to the same eigenvalue lambda, where K is a non-zero scalar. That is one important point. Second one is, the characteristic vectors corresponding to the distinct characteristic roots of matrix A are always linearly independent. The characteristic vectors corresponding to the distinct characteristic roots of matrix A are always linearly independent. Theorems. Theorem number 1. The characteristic roots of a Hermitian matrix are real. Very important bit. The characteristic roots of a Hermitian matrix are real. We will see the proof. Suppose A is a Hermitian matrix. That means A conjugate transpose is equal to A. That is Hermitian matrix definition. And lambda is a characteristic root of A. X is a characteristic vector of A corresponding to the characteristic root lambda. Then A into X is equal to lambda into X. We take this as equation 1. Now we pre-multiply equation 1 by x power theta. X power theta into ax is equal to x power theta into lambda x. We consider this as equation 2. Ax is equal to lambda x, equation 1. After pre-multiplying both sides of equation 1 by x power theta, we take this as equation 2. Now we apply conjugate transpose on both sides of equation 2. X power theta ax whole power theta is equal to x power theta lambda x whole power theta. Now we write this in reverse order. X power theta, a power theta, x power theta whole power theta. We bring this scalar outside. Since this is a scalar, no need of finding transpose. Just we find out only conjugate. So lambda bar. We write these two matrices in reverse order. X power theta whole power theta. Since A is Hermitian matrix, a power theta is equal to A. Now we replace a power theta by A. X power theta, a power theta is replaced by A. X power theta whole power theta is nothing but X. Lambda bar, x power theta whole power theta is X. We consider this as equation 3. Equation 2. From equation 2 and 3, we observe LHS are same. Therefore, RHS are equal. Therefore, x power theta lambda x is equal to lambda bar x power theta into x. From 2 and 3, we observe LHS are same. So, we are equating RHS. Now, we bring this lambda outside this. Lambda x power theta into x is equal to lambda bar into x power theta into x. We bring this term to the left side. So, taking x power theta into x common, lambda minus lambda bar into x power theta into x is equal to null matrix. Since x is a non-zero vector, x power theta into x is not equal to null matrix. This is a non-null matrix. So therefore, since this is not equal to null matrix, lambda minus lambda bar must be 0. Therefore, lambda equal to lambda bar. Since this scalar is equal to its own conjugate, that number is a real number. So, characteristic roots of Hermitian matrix are always real. So, important bit in competitive exams, this is what are the characteristic roots of Hermitian matrix? They will ask. Therefore, the characteristic roots of Hermitian matrix are always real. The second theorem, theorem number 2, the characteristic roots of skew Hermitian matrix are either purely imaginary or 0. This is also very important bit. How we will see? Proof. Suppose A is a skew Hermitian matrix. Suppose A is a skew Hermitian matrix. Then I into A is a Hermitian matrix. So on multiplying this matrix with IA will become Hermitian matrix. Let lambda is a characteristic root of matrix A. For this skew Hermitian matrix, lambda is a characteristic root. Then A into x is equal to lambda into x. We multiply both sides with I. IA into x is equal to I lambda into x. This implies I lambda is a characteristic root of IA. I lambda is a characteristic root of IA. What we have seen, IA is a Hermitian matrix. Therefore, I lambda is a characteristic root of Hermitian matrix. So actually A is a skew Hermitian, but IA is a Hermitian. Just now we have proved in theorem number 1, the characteristic roots of Hermitian matrix are real. That means this is real. I lambda is real. In order to get I lambda is real, lambda must be purely imaginary. So to get I lambda is real, lambda must be purely imaginary or 0. That is why the characteristic roots of a skew Hermitian matrix are purely imaginary or 0. These two are very important bits in competitive exams. In the next session, we will see some more theorems, some more important questions. Hope you understood this class. Thank you.